All right, I believe you're able to see my slides now. Okay, so thanks for that introduction, Sonia. Always good to see you. Today, we're going to be talking very specifically about one piece of the geographic calculator. There we go. So this is me. I'm Sam Knight. I'm the Director of Product Management here at Blue Marble. I've been with Blue Marble for rather a long time. And I've been working with users for a very, very long time. One of the things we try to do is to solve very complicated problems that arise in the world of geodetics. These problems exist between any different software you might be using within different use cases, but the coordinates are really the base of everything. So what we try to do is make handling the coordinates a trivial part of the equation. It's very complicated stuff, but we try to make it easy for our folks. Today, we're going to be talking very specifically about one type of coordinate system, and that is the local coordinate system based on ground locations rather than geodetic things like horizontal datums and such. So within the context of a local coordinate system, they don't need a GPS. They don't need any larger map of the world. They don't care about anything beyond the very localized area on the ground that these coordinates represent. They have all different sorts of purposes, from the mining industry to oil fields, forestry applications, construction, and so on, many applications. But dealing with these coordinates can be rather challenging without a specialized tool that is designed to work with those. So what we're going to be looking at today is our product called the Geographic Calculator. It essentially is a geodetics conversion package. If you're not familiar with the calculator at all, it specializes in data reprojections, coordinate transformations, so moving coordinates from system to system, unit conversions, and all of those very granular level management tasks that you have with dealing with geodetic data, or simply coordinate data that is not geodetic in this case. We pride ourselves in making a very comprehensive tool that is up to the challenge of most of the complicated geodetics tasks that we have in the world today. So that's the Geographic Calculator. And today we are specifically going to be looking at how we handle local coordinate systems within the context of the Geographic Calculator. So I talked about a few use cases: surveying, construction, mining, airport management, and so on. The coordinates that we're dealing with are all common. It really doesn't matter which of those applications it's going to be, because the work is being done by surveyors. It's typically done to a survey grade level of accuracy. It's very high quality data. It's usually also very important data. So it's important to get it right the first time. Sometimes it involves field work, sending the surveyors back out to collect control in an area that needs to be improved based on what we're going to be deriving here. But the fundamentals of these are common across all of the use cases. So this is a ground-based coordinate system. There is no geodetic datum associated with it, no model of the whole world underlying. These are simply based on a pin in the ground very commonly, or a survey benchmark of some sort. In some cases, it's something as simple as a tree or a rock. There is an arbitrary location on the ground that is assigned 0, 0 for the coordinate positions, and then it is aligned very commonly to magnetic north or true north, or even just some other local axis. So the coordinates themselves are geodetically dumb. They do not have any relationship to the rest of the planet in the same way that we do when we're working with, say, a latitude-longitude coordinate system, or a projected coordinate system, or an Earth-centered Cartesian coordinate system, for example. So the mathematics that are involved with these are fairly complicated and fairly specialized. We're going to be using polynomial equations, and what we're going to do today is actually derive a transformation between a local coordinate system that has no geodetic control and a global system, such that we could maybe use a GPS to locate positions within that space. Conceptually, what we're going to be doing is very similar to the idea of georeferencing. So if you have something like a raster image that's maybe freshly scanned off of an old paper map or something, or an aerial photo that has not yet been rectified and put into a particular projection or latitude longitude system, we are going to isolate spots in the coordinate space. And in this case of a raster image, it's the pixel coordinates within the image. What we're going to be doing is mapping up a grid of arbitrary coordinates, and they're just as arbitrary as pixel locations. They just happen to be based on some position in the real world. We're also going to have a second set of control points, and those would be the reference points, say, that we have on the right-hand side over here on our raster image, that's based on actual map data in some projection or latitude longitude. If you've ever done georeferencing of a scanned raster image, this is very much the same process. It's just not quite as visual. So this is the process we're going to be stepping through today. So here we are in the Geographic Calculator. If you are an existing user, if you're already familiar with this application, the Geographic Calculator, we're going to be working within the best fit job, and that is one of our point database jobs that we have. There are many different types of functions that we have in the Geographic Calculator. Today, we're just going to take a deep dive on the best fit job. Within this data, what we have are two coordinate systems. So we have control points that have been surveyed within the local coordinate system. That's going to be our local northing and local easting. And then we also have control points that were surveyed at those same locations. So for a given coordinate in our local system, we also have a projected coordinate. And in this case, our coordinates are within a UTM zone, a very, very common surveying system for where this particular data lives. This data is actually real data. It came from a mining grid operation. We have simply picked it up and moved it to protect the original owner of the data that allowed us to have this stuff. So this is based on real field surveys. And all we need to start off with is a spreadsheet. And in this case, we're using just a simple Excel sheet. And we just need columns for northing and easting in our local system, and then a second set of columns for northing and easting within our UTM system. The specific coordinate system that the control points are in is not actually important. It can be in any coordinate system you need it to be. It could be in any lat long system, could be in any projected system. We just need to know what that system is. So the process here is basically going to be to say that the coordinate in our local north and local east column is the same position as the coordinate in our UTM 15 north and east columns. Then we're going to derive a mathematical model that's going to allow us to move back and forth in between those. And the type of model that we're going to be starting off with is an affine transformation. It's a simple linear polynomial style equation. So basic mathematics that are, on the level of secondary school mathematics. Nothing too complicated here. The good news is you don't actually have to do the math. You don't even really need to be particularly familiar with the math. That's what this tool is going to do for us. To begin, we need to define what coordinate system our control points are in. So this is our UTM 15 north and east columns. The names of the columns here are just what was entered with the data. So it doesn't tell us anything that we can read. So the first thing we need to do is select our projected coordinate system. And so to do that, we're going to get into our database of coordinate systems. And in this case, I'm going to go down under the projected folder. I'm going to take a look in the UTM folder. And this data just happens to be based on WGS 84 in zone 15 north. So I've set my input coordinate system here to match up to what I have as my geodetic control. The next step is to define all of the columns across that spreadsheet for where we're reading our data from and where we're going to write out some error factors that we're going to be calculating. Down at the bottom, going from left to right across the screen here, we have, first we have what's called the use flag. And this is essentially a switch. We're going to use this column to determine whether or not a particular control pair should belong into the model that we're calculating at the moment. You don't need to have this in your data to begin with. If you don't have it, you can just say add new column, and it will populate a new column, and it will be full of ones. So the way this works is if there is a 1 in that value, it's going to use the coordinate. If there is a 0 in that column, it is not going to use the coordinate. There is a name field that is optional. Survey data very often has some type of coded name or number associated to identify particular control points. In this case, our data doesn't have that, so we're going to leave that blank, and our points will simply be identified by the row number that they appear in. The math transform at the bottom. This is probably the most complicated thing to think about conceptually, but there's nothing really here to make a hard decision about. The math model for most of these is going to be an affine transformation. It's a linear polynomial. It requires a minimum of 3 control points. However, more commonly within real survey data, we typically use networks of 20 to 30 control points that are well distributed around the area that we're surveying and we're working within our coordinate system. If you are expanding beyond the level of, say, 15 kilometers, 15 kilometers is a bit of a breaking point. If the area that you're mapping goes beyond that, then we start to need to move up to more advanced control sets. So we might move up to second order polynomial. If you move up to very large sets, all the way up to the size of entire countries or continental regions, then we're going to be all the way up to things like fifth order polynomial. Much more variables taken in place, much more advanced mathematical transformation that goes. But most of these coordinate systems that we use are very localized, and an affine transformation is going to be suitable for just about any purpose we would have within survey level accuracy. The rest of these fields, we're simply going to match up to the local north and local east columns. So we put in our original control points that we're going to be transforming to a new system. We put in our the geodetic control. So in this case, this is our UTM columns. So the second set over here, that allows us to match these up and figure out where the common points are. And then the remainder of the columns, these are residual errors, and these are going to be calculated. I've put them in my table already just to save a little bit of time. But if you need to add these, you can simply add a new column to the field. So I'm just going to quickly put these all across. And then lastly, we have an error threshold. So we're going to be calculating some errors. The default value here is 3 times the root mean square error, and that typically works very well. Some people will drop that down to 2. Some people will put it at about 2.5. But what that does is it is a statistical error that scales based on the relative accuracy of the entire transformation that we're going to be calculating. The root mean square error is effectively like the average accuracy throughout the area that we're going to be modeling. This value as a default works very well, so I'm going to leave that right set as it is. Lastly, the name up here of the coordinate system, we're going to be creating a new coordinate system in the database. So we can name that whatever we want, and I'm simply going to call this Sam's grid. Once we're done with that, we go ahead and hit process. And this will calculate this equation to map these two coordinate systems together. The visual output that we see is simply a lot of very small numbers. Each of these are the vectors of the X and the Y error within the model that we've generated. So we have a linear polynomial transformation, and these represent the error vector of where a given point is expected to be based on the average of the entire model together. It's a lot of numbers to look at, so it doesn't really have a whole lot of visual impact for us. Very often it's hard to pick out an individual error. So the way we view this is on a different plot. So we're going to plot these out graphically, and it gives us a much easier way to assess where our outliers are. So all of these points are representative of the locations within each coordinate system. So within the local coordinate system is our forward direction of this equation, and then flip the equation around. We're going to go back the other way. That is the reverse direction. And you'll notice that the vectors coming off all of these points simply go in opposite directions as we move back and forth through those mathematics, whichever way we're calculating, from local to global or global to local. These tails that come off of the points are how we visually assess where our largest errors are. So these are multiplied. These are exaggerated tails simply to give us a visual representation of where those relative errors are. The ones with the small tails are very tight. The ones with the long tails are looser. The RMSE over here, that is the root mean square error. And that is a linear error that's sort of summed up for the entire area of the map, sort of the average error of all of the points together. And that is in the input units. So our input units here are meters. So our root mean square error for the entire transformation area is about 10 centimeters. The exaggeration factor below that, this is the multiplication that we're doing to visually mark out how far off we are. This is being multiplied by 3,000 in order to make a tail big enough for me to see as a human looking at the screen. It does a very good job of telling me that that point is the one that is the worst in our model. And if I grab our selection tool and click on it, I can get the full information about that point. So in this case, I see that it has an X error. So it's almost purely an X error in the east direction of about 27 centimeters. That's not particularly survey grade accuracy. So it could indicate that there is a problem with that particular point. Maybe I want to send a surveyor back out into the field to make sure that those data points actually do have a high level of accuracy and double check them. We can very quickly see that point number 21 there is a big error. Point number 20 and also point number 7 are sort of suspect. Now we would do this in an iterative process. We would take one point out of the model, maybe send a surveyor back out to check it. Maybe we eliminate it from the model and then recalculate. So what we do is go back to the best fit job itself. We scroll down to point number 21 over here. And I'm simply going to change that value, the point use flag, to 0. So that we're going to take that right out of the model. And I'm going to reprocess the job. It's just simply going to prompt me that I'm overwriting the previous run, and I'm going to say yes to that. When we do that, you'll see for point number 21, its error is now changing because we took it out of the model. The rest of the errors have all dropped as well. So if we go to the error plot, you'll see the representation of that point has changed. There's a little legend up here to tell us exactly whether it's in or out of the model and whether or not it's an outlier. The accuracy for the entire RMSE has dropped. So it's about 8.7 centimeters now. So we improved the fit of the entire model by excluding that one point. Maybe I want to double check that and have some surveyors go back out into the field and verify that that really is a bad point, but we can work with that. I can keep on doing that. So I can go around, I can assess, point number 20 that we saw before. I can assess point number 7 that we saw before, and we can build the accuracy of the fit of these two grids as we derive our transformation in between them. Depends on the overall level of accuracy that we're looking for. If we want the highest levels of survey accuracy, we would probably maybe need to verify some field work on this. If not, we could simply try validating this with some transformations of real data, if we had some other checkpoint data, for example. Once we get this to the point where we're happy with the RMSE being within the level that we need for the transformation that we're doing, that permanently becomes a piece of your Geographic Calculator installation. So within the database of coordinate systems, we see my new grid that I just named. So there's that SAM's grid that I entered. And we can see all of the parameters that we have derived to fill out the coefficients of an affine equation. This again, I said, becomes a permanent piece of the Geographic Calculator's database. You can save this right in place. And that's all it takes. It's now part of my installation. And from there, I'm free to do things like move to an interactive conversion job. And I can find that coordinate system for input or output. I can do whatever I need to validate the transformation of individual coordinates from any coordinate system into our localized grid that is on the ground for just that one part. That's basically how simple the process is. The main things on the Geographic Calculator doing this process takes just a couple of minutes to derive one of these transformations. The biggest part of the input is validating that you've got good controls going in. And that's where maybe you go out into the field again, maybe you send your survey crew out to check some of these points. But assuming you have good quality data to feed into this process for your local coordinate system, it's a very, very trivial exercise to map up this transformation. And you can then apply it to any type of data. So whether it's an individual coordinate, whether it's a vector file like an Esri shape file or say an AutoCAD DXF file, any raster format or any point database format as well. I think that's all I've got now for time, and I think I'll hand it back to Sonia if we have any questions.